In this lesson, I want to talk about sequences, particularly arithmetic and quadratic sequence. Let's start with the arithmetic sequence. Could you remember to subscribe to the channel and turn on the notification bell so you can receive a video as soon as it's released and you can enjoy a new lesson every day. Arithmetic sequence, we have a sequence where the numbers go up or down at the same rate, or I should say by the same number. Say 6, 11, 16, 21, 26, etc. I will call these my term number 1, term number 2, term number 3, term number 4, term number 5, etc. The purpose of this question is to find the nth term. What formula I can produce out of these numbers, so when I replace n in that formula as 1, it creates 6. When I replace n with 3, it produces 16. So in order to find the nth term, I'm going to find the first difference. The difference between the numbers, so I know but what number they've gone up. So 11 take away 6, 5, 16 take away 11, 5, 21 take away 6. Unless these are the same number, all 5s or 4s or 3s, we will not have an arithmetic sequence. That is the whole definition of arithmetic sequence, that the numbers go up or down by the same value, same constant value. Therefore, the nth term of this sequence starts with 5 followed by n. So I use one of those and multiply this by n. So then I check, would 5n be enough to produce the numbers I want by replacing n as 1 or n as 2? I check, when n equals 1, I end up with 5 dots of 1, which is 5. And that means I'm short of 1. I need to get 6. So what I do, I write my nth term and I complete it. Because 5n plus 1. Now check it with another term. Give n 2 now. 2 lots of 5, 10. Add 1, 11. Yes. Term number 5. 5 lots of 5, 25. Add 1, 26. So this n term is correct. To find that extra bit here, we can do a different method. Let me just write this sequence again. 6, 11, term number 1, 2, 3, 4, 5. Same as before, the first difference. Instead of checking to see whether this nth term equals 5n is complete or too much or too little, I go and find the 0th term, term 0. Means I am going to go back one step. What number, when I added 5, gave me 6? 1. So I add the 0th term to my formula. So this is now a complete formula for the nth term of a arithmetic sequence. Let's have another example. This time 21, 17, 13, 9. These are my sequence of numbers. And it is arithmetic sequence because the numbers are going down by same constant. So if I say the first difference here would be 17 take away 21 minus 4 minus 4 minus 4. So the nth term would have been 1, 2, 3, 4. And I'm going to go back to find the 0 term. Before that, I write my nth term, which is minus 4n. That number, one of these, written here, followed by n. To find whether I need to add or remove something from here, I go back one step to find the 0 term value. What was the number when I removed 4 became 21? It was 25. So I'm going to add 25 to complete my nth term. So the nth term can be written as, starting with the positive term here, 25 minus 4n, or minus 4n plus 25. Let's check. Say n is 3. 25 take away 4 lots of 3. 25 take away 12 is 13. Yes, term number 3 should be 13. I can now use this formula to find any term. So, for example, what is the 10th term of this sequence? Be 25 minus 4 lots of 10, which is 25 minus 40, it'll be minus 15. This concludes our lesson on arithmetic sequence. I'm now going to take you to quadratic sequence. Now going to quadratic sequence. There are two methods for this. Using method 1, I want to find the nth term. Maybe put here nth term so you remember. Of this sequence, which is 10, 21, 38, 61, and 90. Of course, this goes on and on and on. Let's put numbers above them. N equals 1, 2, 3, 4, 5, etc. As before, we're going to find the first difference. So first difference here, 21 take away 10, 11. 38 take away 21, 17. 61 take away 38, 23. 90 take away 61, 29. You can see the first difference is not the same, the change. So what we do, we're going to find the difference of the first difference. Find their difference. And it should give me the same value. If it doesn't, it's not a quadratic sequence. 17 take away 11. 23 take away 17. 29 take away 23. 6. 6. So the second difference is a constant value of 6. In order to begin our nth term, always, we divide our second difference by 2. That produces 3. Therefore, my quadratic sequence starts with 3 n to the power of 2 because of the second difference. So, therefore, 3n squared so far. Now, part of these numbers are obtained by 3n squared. I want to know what is left over. So I start my sequence again. The same original numbers. And see what 3n squared achieves by giving n these values. So just remember again, n was 1, 2, 3, 4, 5. I'm giving n value 1. 3 lots of 1 squared is 3. 2 squared is 4. Times 3 is 12. N is 3. 3 squared is 9. Times 3, 27. 4 squared, 16. Times 3, 48. 5 lots of 5 squared, 25. Times 3, 75. Then I'm going to take away. So these are my leftovers now. 10 take away 3. 21 take away 12. 38 take away 27. 61 take away 48. And 90 take away 75. I call these my leftovers or the remainders. So say leftovers. We need now to make a pattern, the nth term out of this pattern. So these are my new numbers to make the nth term from. Let me just copy them again. So I've got room to put the values of n. And when I find the first difference, two, 2, 2, 2. So it's a linear. Therefore, nth term for this part equals 2n. Is that complete? Look, or the first example I gave you on linear or arithmetic sequence. Let's go back one step to find the zero term. The zero term would have been 5. 5 plus 2 makes 7. So I'm going to add to my 2n. So the nth term for the leftovers is 2n plus 5. Therefore, the complete nth term would be the nth term from here added to nth term here. Therefore, the complete nth term equals 3n squared from first part plus 2n plus 5. So as you can see, it's a quadratic nth term, where the highest power of n is 2. One more example on quadratic sequence, finding their n terms. Say in this case, we have numbers -1, 2, 11, 26, 47, etc. I'm going to use again the method 1. I haven't shown you the method 2 yet. I'm going to find the first difference. Let's number the terms. Term number 1, number 2, number 3, etc. We'll find the first difference. So 2 take away minus 1, 11 take away 2, 26 take away 11, 47 take away 26, which would be 21. So that's my first difference. As you can see, the first difference aren't a repeating constant. So I'm going for the second difference. Six. Okay, my second difference is a repeating constant of 6. Could be anything. Whatever it is, we have to divide by 2. So that becomes 3. Therefore, the nth term so far is 3 followed by n squared. As I explained in the previous example, 3n squared will produce some of these numbers, maybe not all of them. Let's go and see what are the leftovers. Start again with the sequence we have. And see what does 3n squared produce. Again, three n squared, when n is 1, produces 3. When n is 2, 12. When it's 3, 3 squared, 9 times 3, 27. 4, 16 times 3, 48. 5 squared, 25 times 3, 75. I'm going to take away. I'm looking for the leftovers. Minus 1, minus 3, minus 4. 2 take away 12, minus 10. 11 take away 27, minus 16. 26 take away 48 is minus 22. 47 take away 75 is minus 28. So these are my remainder, or as I call them, leftovers. I need to make a pattern, the nth term out of this pattern of the leftovers. I write this pattern again. Find the first difference. Minus 10, minus 4. That's minus 6. Minus 16, minus 10. Minus 6. Minus 22, take away minus 16. And the same here. Therefore, we have a linear sequence for these numbers. So the nth term for this part equals minus 6n. Let's go to the 0th term to see if we have to add, subtract anything to this number. Go back one step. the zero term would be minus 2. Oh, sorry, plus 2. Plus 2, take away minus 6, give me minus 4. So I'm going to add the zeroth term here. That would complete the nth term for this part, the part for the leftovers. Therefore, the complete nth term would be the part here and these two put together. Three n squared from the first part plus that minus 6n plus 2. Now, don't always expect to have a complete quadratic. Sometimes you have the n squared term and the constant. Sometimes you have the n squared with the n term and no constant. I'll give you a couple of examples on this, so you don't always expect to get values for n and the constant. Let's look at the next example. Set of numbers 0, 2, 6, 12, 20. Let's give them the n values. Term number 1, 2, 3, 4, 5, etc. Let's find the first difference. 2 take away 0, 6 take away 2, 12 take away 6, and 20 take away 12. So that's my first difference. And as you can see, it's not a repeating constant. So I'm going for the second difference. The second difference, 4 take away 2, 6 take away 4, 8 take away 6. Now we have a repeating constant. That number, whatever it is, I need to half it. Divide by 2, 1, therefore 1 n squared so far. Or we could just say n squared. Some of these values in the sequence are responsible for n squared. We want to know how much of these numbers is obtained by n squared and what is left over. So I start with my set of numbers again, original numbers, and find out what n squared is producing. Giving numbers again, 1, 2, 3, 4, 5. Finding the first difference. No, sorry, finding what values of n squared is produced. When n is 1, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, and 5 squared 25. Let's find the leftovers. 0 take away 1. 2 take away 4, minus 3, minus 4, minus 5. These are the leftovers. Now, let's make a pattern out of, and sorry, not a pattern, the nth term out of the leftovers. Again, as before, we always give them n values, 1, 2, show me the term number. Let's go for the first difference. Minus 2, minus 1, minus 3, minus 2. You can see the first difference going to be minus 1, minus 1, minus 1. Therefore, the nth term for this part is minus 1n. Let's go to the 0th term. And that would be 0. So add 0. So equal just minus n then. Adding these two nth term together to complete our nth term for the whole sequence. Therefore, the complete nth term equals n squared minus n. As you can see, it's not a complete quadratic expression or a formula. Our constant here is missing, is 0. Or not always guaranteed we have a number here. Let me give you an example where the n term doesn't exist, but the constant exists. If we look at this set of numbers, minus 1, 5, 15, 29, 47, 69. Let's go for the first difference. That would be 5 take away minus 1, 14, 47 take away 29, and 69 take away 47. So as you can see, the first difference is not the same number. Let's go for the second difference. So let me just label as first difference, now second difference. 10 take away 6, 14 take away 10. They all produce second difference of 4. Dividing 4 by 2. Therefore, 2n squared so far for our nth term. Let's write our set of numbers again. And look for the leftovers now. Let's see what 2n squared produces. When n is 1, 1 squared times 2. When is 2, 2 squared times 2. 3 squared times 2, 4 squared times 2. 5 squared times 2. 6 squared times 2. Let me just put these n values. 1, 2, 3, 4, 5, 6. So 6 squared, 36 times 2, 72. So I'm going to take away to see what is left over. Minus 1, take away 2. 5 take away 8. You can see the difference is all minus 3. So I can make a pattern out of these. It's already a pattern. I can find the nth term. So the complete nth term equals the first part of the formula together with the last part, which is just minus 3. Again, you can see here, it is not a complete quadratic, the nth term doesn't exist, but still called a quadratic sequence because the highest power of n is 2. Our next lesson going to be the second method, which in my opinion is much quicker and much easier to use in order to find the values of n squared, n, and the constant by just looking at the first and second difference. I hope you understood and enjoyed this topic of sequences so far. My aim is to make maths as enjoyable as possible for you. Until next lesson, bye.